Sushruta for NEET is now available on the Google Play Store. Try it out for free.
So, hi students. We continue with our discussion of heat and the theory of gases. Last time we looked at the whole ideal gas equation, etc. This time we're going to look at kinetic theory of gases. Okay. So, kinetic theory of gas is a recognition that the temperature is related to how fast the molecules move around. Okay, so that's why it's called kinetic theory. So they're saying that how fast the molecules move around determines the heat contained and the temperature. Okay, and therefore that is the whole thing. Okay, the absolute temperature of a given sample of a gas is proportional to the total kinetic energy of its molecules, or K equals half mv/Rms squared, right? So understand the thermal properties of matter and connect that to the corresponding equations of state, that is PV equals nRT, right? So now, therefore, there is a certain amount of we all have heard of this 6.023 into 10 to the power of 23 Avogadro's number, the number of molecules in a mole, right? So now, to explain the kinetic theory of gases, consider a cubic box of length 1 with the gas molecule of mass m moving along the x-axis with velocity v. Therefore, its momentum is m times vx. Okay? Moving along the x-axis with the velocity vx. Therefore, its momentum is m times vx. The gas molecules collide with the walls. At wall 1 collides, and then its momentum changes. Similarly, it collides with wall 2, and then its momentum reverses, right? So thus the change in momentum when it hits the wall is given by 2 mvx. After the collision, the thing travels a distance of 2l before colliding again, right? So thus the time that it takes is the distance traveled 2l by the velocity. Now the force is the change in momentum divided by the change in time, right? So now, if you look at the change in momentum, right, it's 2 mvx. We already did that calculation here, right? 2 mvx delta p, and then the corresponding time is 2l by vx, right? So 2 mvx divided by 2l by vx is delta p by delta t, right? So that is roughly mv square by l. Okay. Now the continuous collisions also exert pressure on the wall. So that is the force. The force divided by the area will give you the pressure. So the force we calculated there, mv square by l, and you divide that by l square, then you end up with mv square by l cubed, okay, or mvx square by l cubed. Okay, so that is the result that you end up with. Now, know that the gas is made of n molecules and move in all possible directions. The pressure exerted on wall 1, collision of n number of gas molecules given by nl cubed times v square, right? So now pressure is now the average velocity of all gases colliding with a wall. Let's say that is you write that as as v square equals vx square plus vy square plus vz square, right? Therefore, when the pressure exerted on wall 1 is given by all the molecules that go and push on wall 1 per unit area, right? And therefore that's the whole the whole way this calculation is done. Okay. So now, for a large number of molecules, you can say that roughly Vx square, Vy square, and Vz square are equal, and they are therefore Vx square plus Vy square plus Vz square equals V square, right? And therefore you can say it is 3 times Vx square, right? V square is 3 times Vx square, therefore it is 1 by 3 V square, so 3 dimensions, right? So now we can therefore say, that by rewriting this equation and writing and plugging it back in, where V is the volume, L cubed is V, right? So then by plugging it back in, you end up with the equation PV equals NMV square by 3. The V square by 3 came because it was Vx square plus Vy square plus Vz square, and Vx was equal to Vy was equal to Vz because of symmetry, and that was therefore equal to 1 by 3, right? So therefore the pressure on one wall was 1/3, right? Therefore 1 by 3 NMV square. So this is a very important rule. It is N times PV equals nRT. Therefore it N 1 by 3 mv square is also the same as RT. So nRT equals 1 by 3 nmv square, right? Therefore, that is the PV equals nRT is the ideal gas equation from our macro studies before, right? For Charles' law, Boyle's law, coupled together gives you ideal gas equation. PV equals nRT. R is the Boltzmann constant, 8.3 into the power of something, right? Or and K is n times K is called the Boltzmann constant, right? So so PV equals nRT, R is 8.314, and K is 1.3 to the power of minus 23, and therefore you end up with the equation, right? So now when we look at the VRMS from this, right? So we therefore say 1 by 3 mv square equals RT, right? The n cancels, 1 by 3 mv square equals RT, and you take the roots, then you therefore end up with 3 RT over M is the VRMS. Therefore, the VRMS is 3 RT over M. Therefore, you can also write it as 3 by 2 RT. The average kinetic energy is half mv square. That becomes, therefore, you end up with 3 by 2 RT is the average kinetic energy. Okay, so now we all know that the average speed will be less, right? Therefore, the average speed is 8 by pi. It's not that much less, right? 8 by pi versus 3 is how much? 8 by pi is only slightly less than 3. Okay, that's the point there. So the RMS speed, root mean square speed, is 3, while average speed is 8 by pi. Therefore, you end up with this 3 RT over N. Okay. So this is the basics of your kinetic theory of gases. But kinetic theory of gases is actually quite complicated when you do bring in a lot of real ideas as well. And most often they try to push the envelope on bringing those real ideas into play. Okay. So now there was a lot of discussion around this over the years, and in fact, it paved the way for other kinds of sciences. The kinetic theory of gases is actually a very elemental science, which then led to a lot of statistics, which entered physics, and then it revolutionized the physics in the end. So now we therefore have this idea of what is called equipartition of energy. Now we have multiple degrees of freedom, right? Now, what is this degrees of freedom, right? If you had a single atom in a 3-dimensional space, it can move freely along the x, y, and z, right? Up and down, left and right, forward and backward, right? So that is, therefore it has three types of movement, translational movement. No? If you specify the location of this atom, you need three coordinates, right? You can also say that a single atom has 3 degrees. So monoatomic molecules have 3 degrees of freedom. Now let's imagine a diatomic molecule like O2. Remember that O2 is diatomic, N2 is diatomic. So a lot of the gases are either O2 or N2. Carbon dioxide, in fact, is a very small part of what we have. As you know, and as I discussed before, the amount of carbon dioxide in the Earth's atmosphere has increased from 290 parts per million to 420 parts per million today, right? So now, similarly, but then when you have two molecules, apart from the three translational degrees of freedom, these molecules can also rotate around the center of mass. Two such rotations are possible along the axis, normal to the axis, right? So you have only 2 degrees of freedom in the case of an O2 molecule, right? Two such rotations are possible along the normal axis, so that joins it. This adds 2 additional degrees of freedom. So in some sense, there are, what do you say, 5 degrees of freedom, because you have rotation as well as translational motion. So in simpler words, specify location of the molecule, you need, important note here that the diatomic molecules are not rigid rotators. Along with the translational rotation movement, you can also oscillate. This adds a vibrational degree of freedom to such molecules. Hence, to specify the location, you need to finally find X, Y, and Z, and vibrational quantity. So, in a nutshell, degrees of freedom is nothing but the number of ways in which a molecule can move. So, this forms the basis of this idea called equipartitional energy. The law of equipartitional energy says the total energy of the molecule is divided equally among all degrees of freedom. If you have more degrees of freedom, then you will have less energy per degree of freedom. So before delving into the calculation, let's understand the law better. If there is 1,000 units of energy, 5 degrees of freedom, then the molecule allocates 200 units of energy to each motion. So what does that tell you? Right? So there's less per degree of motion for a diatomic molecule. Right? So now let's look at the monoatomic molecule first. Gases in thermal equilibrium has at a temperature T, the average energy is 3/2 kT. We already did that. So we already came half mv square, half mv square, half mv square, half kT, half kT, half kT. Each mv square gives you a half kT. Okay. So now, therefore, since there is only translation motion, the monoatomic molecule, the energy allotted to each molecule is half kT, and there are 3 types. Now, in the case of a diatomic molecule, the translational, rotational, and vibrational movements are all involved. Hence, the half mv square, half mv square. So for translation, plus half I omega square plus half I omega square for the 2 rotational motions. So you have 5 degrees of freedom. This is what he's saying. And omega 1 and omega 2 are the angular velocity. The energy component of vibrational motion is also included, right? And as a result, according to law of the total energy is among all the energy modes. While the translation rotation contribute half kT, the total vibrational energy contributes 2 times 1 kT, since it has both kinetic and potential energy modes. Okay, so so you have the 3 modes plus 2 additional modes, right? So on the basis of kinetic theory of gases, so now if you had a question involving, say, a monoatomic molecule like an inert gas, helium or argon or neon, they will exist as a single monoatomic. Okay? But if you had hydrogen or oxygen, they will exist as a diatomic or a nitrogen, right? On the basis of kinetic theory of gases, assume the molecules of a gas are continuously colliding against each other. They all hitting against each other, hitting against the wall, etc. Molecules move in straight line constant speeds between, therefore they follow what is called a kind of Brownian motion. So the mean free path is the average distance traveled by molecule between two successive collisions. If S is the total path traveled in n collisions, the mean free path is S over n collisions. Total path divided by the number of collisions, right? Will give you the mean free path. What is the total path divided by the number of collisions? That will give you the mean free path. Expression for the mean free path. Consider gas containing n molecules per unit volume. We assume that only one molecule is under consideration in motion, while all the other molecules are at rest. Sigma is the diameter of each molecule. Moving molecule collide with all these molecules, where centers lie within a distance. Okay, so it will collide with everything that's close by, right? Where centers lie within a distance from its center as shown. Okay? So it will collide with a set of molecules which are only this distance apart. V is the velocity of the molecules. Then in 1 second, it will collide with all the molecules with a distance sigma between the centers. 1 second sweeps a volume pi sigma square V. Okay, because he uses a cylinder, pi sigma square V. Okay, where sigma square is the radius and V is the height of the cylinder, because it travels translationally this much, right? And it vibrates by sigma. V is the distance traversed by molecules in 1 second. The mean free path total is equal to total distance traversed in 1 second by number of collisions. Therefore, you end up with 1 by pi sigma square n. Okay, so 1 by pi sigma square n will give you the average, will give you the mean free path. Okay, that is assuming it's a cylindrical assumption, right? So this expression was derived with the assumption that all molecules are at rest except the one which is colliding with the other. So this is the second part of the second derivation. This mean free path derivation is the second derivation with respect to the kinetic theory of gases. So now we are going to look at a third idea. This third idea is what happens if it's not you can't make ideal assumptions, non-ideal assumptions. And so what happens, okay, in a non-ideal gas? So that's the third link there. Okay, you can take a look at this YouTube to better understand this material, because we don't do as much justice as that lecture does, because that lecture discusses this in much longer time. So now the specific heat of a substance is the energy required to raise the temperature of 1 kg by 1 degree. Q is equal to ms theta, right? So C equals Q by m theta, right? Or m delta theta. Ms delta theta equals Q, right? Therefore, Q divided by m delta theta will give you C, the specific heat capacity, right? So now let's now discuss some of these other terms. Okay, the first term is this term called enthalpy. Okay, enthalpy is defined as E plus PV. Okay, so now enthalpy is kind of a measure of the internal heat content, right? The energy that is held in, right? E plus PV, right? And therefore, but we already know that PV equals RT, right? Therefore, delta H equals delta E plus P delta V plus V delta P, and that because we are keeping P constant and constant pressure, you therefore end up with delta E equals delta E plus P delta V. Now, so the V delta P is not there because it's a constant pressure, right? Now, therefore, del P delta V, as we know, is R delta T. Therefore, you end up with delta H equals Cp times delta T. Delta E equals Cv times delta T. So Cp delta T equals Cv delta T plus R delta T. So now Cp versus Cv, right? So combine the equation in two black box. So you have Cp and Cv, right? So now, so you have the two types of heat capacity. Now, we already saw this equipartition of energy, and we said that there are 3 degrees of freedom for a monoatomic gas, and there are 5 degrees of freedom for a diatomic gas, right? So now the equipartition of energy states that the energy is P square by 2m, right? P square by 2m is half, is half mv square, and you say mv is equal to P, right? So you end up with half mv square being P square by 2m. So that's the kinetic energy, right? So the specific, so Cp minus Cv for an ideal gas will equal R. Cv is 3 by 2 R and Cp is 5 by 2 R. Okay. Therefore, for in the case of the diatomic molecule, you end up with this idea of 5 by 2 R. Okay. So this is purely the differences in terms of the number of degrees of freedom. You have translational as well as rotational and vibrational degrees of freedom, right? So as a result, you end up with 2 extra degrees of freedom in the case of diatomic molecules, and therefore you end up with 5 by 2 R versus 3 by 2 R for Cv in the case of monoatomic gases. Okay, so now the total energy of the gas is 1 by 2 F, where F is the possible number of degrees of freedom times N times kb. A, you already know Boltzmann, right? P, right? PV equals nRT, total energy is 1 by 2 F times N kb T. Now F is 3 degrees of freedom for monatomic gas, is 5 for a diatomic gas, etc. Okay. So now we already last time we also looked at the mean free path. The mean free path is the distance between collisions, is the average path length between successive collisions. That is given by this formula 1 by 2 root 2 pi d square n over v. My suggestion is this is a little more complicated. This deriving the mean free path, but it's worth learning. Mean free path derivation is a very nice derivation, and it links what you learned in collision theory in mechanics with how we look at gases as molecules which exhibit energy because of the mechanics of their motion. Okay, therefore, and this mean free path is a very interesting idea with respect to the gas molecule and the distance it travels between collisions. Now, one of the ideas was these two ideas which deal with this Leonard Jones potential and the van der Waal equation. Leonard Jones, they came up with this theory that the potential energy is 4 times sigma by r to the power of 12 minus sigma by r to the power of 6 for when it comes to this two molecules, right? And we already see that also in the case of when we look at atomic theory, right? Look at atomic theory, we have weak forces being dealt with using van der Waal, right? So now van der Waal introduced the PV equals nRT. He added 2 factors. One is the A by V by N square and the other is B. A and B are constants. Therefore, he didn't have an exactly PV equals nRT, but he introduced this added factor, which kind of complicated, and this one a constant as well, kind of really complicated PV equals nRT. Okay, so there is a PV equals nRT factor, but then there is also 3 or 4 other factors. Okay, and so and that is part of the complication that was introduced with respect to a non-ideal gas, and they had very good reasons to eventually say that this is this is because of interatomic forces. So excluded volume of radius equal to molecular diameter. So 4 by 3 pi r cubed, right? Is 8 volumes of one molecule. Hence, for one molecule, the excluded volume is 4 times 4 by 3 pi r cubed. Okay. So this correction factor, as it's called, right, is where was introduced by van der Waal. Therefore, you have V minus NB, and then you introduce N also in the numerator. Therefore, you have V minus NB equals nRT. Now, PV equals nRT is slightly changed to in the case of real gases. Okay, so there's a P plus term and a V minus NB term. Okay. That leads to, that is if there is A is basically a pressure correction, indicates some attraction between the molecules. Now, if you have very big A, the molecules are greatly attracted to each other. A very small A means weak forces between the molecules. So why are there these low-level forces? These are, of course, because of the, even in a gas, the heavy neutrons, or not neutrons, the heavy nuclei have attractive forces between the molecules. Therefore, there is some behavior in terms of how they behave. Okay. So finally, when we look at PV equals nRT, normally you have PV equals nRT for a given isotherm. You have a what is that, hyperbola, right? PV is a constant. The hyperbola for a isotherm, right? But here you don't have a hyperbola. You have all these critical point induced equations, which kind of bring into also the question of latent energy, etc. And so there is the motion to liquid and the etc., which kind of really complicate PV equals nRT. So one can say that at a higher temperatures, PV equals as the isotherms move up, you tend to move closer to PV equals nRT. At lower temperatures, things tend to really get very, very complicated. Look at this one, 21 degrees, very, very different from 48 degrees. Okay? Therefore, the isotherms, they behave differently. Therefore, so with that, today I was going to have just a short class and kind of end it, but then I feel that I have not done enough justice to this. So let's maybe spend some time discussing what to do with respect to problems here. Okay? So with respect to problems, in this, right, they will usually give you problems like this. Let me read one problem from Professor H.C. Verma's book. Today, I am also going to take a moment to discuss Professor H.C. Verma. Professor H.C. Verma has been granted the Padma Shri, and as um, a students, you should join in his hard work in writing textbooks for young people and also making them available at a low price so that many students, so his contribution to, of course, he was also an avid researcher and he did a lot of research as well and published many articles which also brought name and fame to the country. But over and above that, he trained a lot of students, and his work as a teacher stands for itself. And his great effort in writing these books, making sure all of you get a chance to buy a very low cost book and not like Rustic and Halliday, or when I was studying, there was no H.C. Verma. There was Resnick and Halliday, and then there was another book called Sears and Zemansky, and now you have a wonderful textbook at a very low cost, you know, and so I thank him, and also it is much more conducive to the way it is covers a lot of material, but without making it too complicated, like uh, you know. Uh, Leslie and Halliday, or of course, Sears and Zemansky was also simpler, but the problem with Sears and Zemansky was very costly, a very thick book, you know. So you have to read more, to learn more. But it's very well written, but you need to have the patience. So let's take a couple of book questions. Let's for a moment first congratulate Professor H.C. Verma, and then take a moment to look at one or two work examples from H.C. Verma. Okay, so here is a question. Okay, a mixture of hydrogen and oxygen has volume 2000 cm cubed, temperature 300 Kelvin, pressure 100 kPa, and mass 0.76. Calculate the masses of hydrogen and oxygen in the mixture. So one equation is PV equals N1 RT by V plus N2 RT by V, right? So now, um, because it has a mass, you can then look at that as well, right? So it has N1 number of moles of this, N2 number of moles of that, right? So N1 times 2 grams per mole for hydrogen, and N2 times 32 grams per mole for oxygen, and so the sum of those two will become 0.76, right? So it's a mixture of hydrogen and oxygen. Then you also have PV equals N1 plus N2 RT. So you have two equations and two unknowns. N1 and N2 are the two unknowns, and therefore using the two equations and two unknowns, you can then solve for N1 and N2. Okay, so now that was the question. Calculate the mass of hydrogen, oxygen, the mixture. Okay, so that's a simpler question. Okay, now there are more complicated questions which deal with this degrees of freedom, etc. Okay, so those are the more complicated questions that you should look at. PV equals nRT. There are a lot of questions that they will ask using PV equals nRT, but they will also ask a few odd questions which deal with this idea of how things work in the context of um, 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 you know pressure and temperature, and how whether it's a 5 by 2 R versus 3 by 2 R, it's monoatomic or diatomic. Okay, and so he gives two types of questions in his book. One type of question is deals with our objective type questions. Okay, and you should look if you're for your JEE mains, you should look more at these objective type questions. For JEE advanced, you should spend little more time looking at the more advanced questions. Okay, so now two closed vessels of equal volume contain air and are connected through a narrow tube. One of the vessels is now maintained at 300 K, the other is 400 K. What will be the pressure in the vessels? Right? So now PV equals nRT, PV equals nRT, right? And so, and then N1 plus N2, right? So, but then in one, the temperature is T1, the temperature is T2, right? The total volume is fixed, right? And N1 plus N2 equals the total N, right? So, given this, you should you should try to do a few questions with TV equals nRT. A lot of questions, that's the main idea, but there are a few questions which do deal with this idea of degrees of freedom and kinetic theory of gases. My suggestion is before you move on, and there are a lot of course, questions dealing with calorimetry, heat loss is equal to heat gain, ms delta theta, ms delta theta. Okay, so try to do some problems involving both these. Okay, and the best way to do these problems is to download our app. Our app now has assessment included with it, right? And we are going to be adding our own assessment as well. So this is a very good time for you to download our app and try it out. Okay? So with that, I'm going to conclude, and I'll see you all again next week for the class 11 people, and we'll continue our discussion. We'll try to discuss next thermodynamics, and we'll go over thermodynamics in a more systematic way than we did kinetic theory of gases. I leave a little bit of kinetic theory of gas for you to read. My suggestion is you spend some time understanding, the collision side, the degrees of freedom side, and finally the mean free path equations. If you do that, and make some notes with it, do some derivations, and then it will make a lot more sense, more detail than I explained it. But then I was trying to cover what was actually 3 classes worth of material in one class. So please spend some time reading and then doing some problems. So with that, I'm going to conclude. I'm going to leave you to get the material right. Sorry about this, but I'm going to leave you to get the material right. Read it again and then understand this degrees of freedom. 3 for monoatomic, 5 for diatomic, etc., and how the whole system works out with this. And today I'm going to conclude early, but then we will continue discussing a little bit of kinetic theory of gases. Again, next class we'll try to do 1 or 2 problems. Then we'll continue with our discussion with thermodynamics. All right. So with that, I'm going to stop today. Then see you again next week.